it sounds like excuse me, a constraint or a requirement or something on the pluggable implementation,
Yes,
that it be able to manage temporal um, space between producers and consumers, or
I agree.
interfaces.
I think that's exactly the right way to look at it. Insofar as the implementation must be able to provide certain functionalities for it to work, then I think that it's fair to either make it that support architecturally required for everybody, or if there are cases where it's not supported, then it must be an enumerable trait.
Okay, thanks.
Any other questions, comments? All right. So we track more material that I'm not going to cover today, but about sort of how this interaction works. But we do have notions of incoming and outgoing dependence arcs and how we handle those different cases. And we essentially have different types of those nodes to be able to manage, hey, is it just the dependence that's coming in and out? Am I actually uh, uh, in creating a command and marshaling the parameters and putting in a command queue and signaling the other side to do some work? Those are essentially the two cases of it's just a dependence or there's some work that needs to be invoked. And the different models for, did I start with one graph and sort of partition it across both sides, or were these really two graphs that are interacting with each other and have incoming and outgoing dependence arcs? So all of those cases are intended to be covered. And I think we need to work through some real world examples. We have had some initial design work, but welcome those particular cases, use cases for that. So again, I think a number of the places where we see that it's useful to be able to have this high level functionality is to be able to support retargetability and generality in the ways that we've talked about before, in ways that can sort of span an interface between multiple graphs, multiple targets. So to that end, we have a number of types for different kinds of nodes, different stages of the graphs, different kinds of nodes and descriptors, and I'll go through some of those briefly here. Again, we talked about these three different stages, and we can create graphs at those stages, and we have different kinds of nodes, and we have APIs for these to essentially create, destroy, or clone graphs, or to work on nodes to add them or destroy them or move them from one graph to another, to add or remove edges. These verbs of graph instantiate and invoke, destroying things, getting properties of graphs and properties of nodes, and then operating on things like aggregating a set of nodes based on criteria into a subgraph, or operating on a subgraph and say, hey, now that it's settled down, let's go add some interface nodes where there are edges that cross between graphs, particularly in cases where they may be on disjoint subsets of resources. So the client essentially owns these graph objects and is responsible for the destruction. And you can specialize these, as we've talked about before. Kind of breezing through some of this here. We decided at this point that regarding edges, that it's of the properties, interesting properties we've seen so far are really related to endpoints rather than edges, so we don't create an edge object. There was some question at one point about, well, do you want to communicate some of the properties like between memory or execution resources as to what the bandwidth or latency properties are for moving data or something like that. And we have an architecture for being able to enumerate some of those properties, but again, and using those in cost models, but haven't so far seen a case where that really needs to be materialized as an edge. you can create edges not just at node creation, because the nodes may not exist yet, and so you can add or remove those later, and edges can span multiple graphs. And if you go and move a node from one subgraph to a different subgraph, you don't obliterate all the edges, they'll stay there so that you don't have to go back and re-add the edges. So any comments or feedback on those directions? All right. And one of the things that we did in terms of the design here is that you can have graphs that are hierarchical. And so a node in one graph could have associated with it a whole subgraph. The subgraph's nodes are not nodes in the parent graph, just the node that represents the whole subgraph is. And so if you have sort of properties of a whole graph, you don't have to propagate them up and down sort of a tree of data structures. Everything is kept locally so that you can convert any given node into its subgraph or vice versa, or do substitution at that level and kind of keep things local. And then you can ask at any given graph, hey, what are the roots, so that you can come up with the those that have node dependencies. That's different than different connected components, because a connected component could have multiple roots. So we don't have anything in service of connected components. But if that's important to users, we could add such a thing. And you can ask, hey, what are your outgoing edges? What are your dependents? And get those. But first how many there are, and then get an array of pointers to those things. Any others with graph experience that have any feedback on that? All right, and we want to be able to capture for any given node, what kind of node is this? And what are its execution and memory resources that it uses? And what are the other parameters that you have? And those are mutable at different stages. So when it's at the instance stage, before you invoke, you can change some of the parameters, but you can't change the edges and the kind of node it is, etc. And you also have an ability to be able to, for any given node, to change some of its execution policies and configuration. We'll talk a little bit more about that. So again, we have this notion of one flat root graph. That's just a convention. It's not actually a special object. And being able to aggregate nodes into subgraphs for that. And the criteria that we can think of on which you may want to do that aggregation is to say, hey, everything for the same kind of target, same set of execution resources, group all that together. Or you could say, I've pre-traversed this graph and marked them as red, green, and blue. So gather all the blue stuff together and make that a subgraph for me. And so there's this notion of a generic tag that's available. So any other criteria that are interesting to folks, like connected components or anything else? Giving too much feedback today. We're also working through with, want to work through with real use cases where when you say if a given, suppose a given node, some of them are blue and some of them are green and some of them are blue and green. If you ask for the blues, do you get the ones that are just blue or the ones that are blue or anything else? It's an exact match or a subset criteria. How exactly is it that we want to do that? And go ahead.
I was going to say, what's the use case for move?
That's the next thing here. So suppose you have an incoming stream of work, and at the moment you've accumulated 30 nodes. Suppose these are tasks that are coming in via a heterogeneous executor. And so far I've gotten 30 of them, and I want to chunk those up into groups of nodes that would be issued as a subgraph. And suppose nominally that would be, I'd say, oh, let's do about every 10 or so. As soon as I get 10, or after I've gotten 10, unless there's some other compelling reason, let me just send those guys down the pike and create a subgraph of them, and then I'll issue another subgraph with the next 10. If I come up with some reason why I want to shuffle nodes after that initial partitioning based on some other criteria of locality or something else, I may come up with an initial version, but then rejigger that, and suppose my 10, 10, 10 becomes 10, 9, 11, because I just wanted to move one node from one to another, then I can do that.
So it's a matter of dispatch granularity, rather than some logical mechanism whereby one node belongs with another graph or something like that.
If your first criteria was based on rough dispatch granularity, and then once you had that, you wanted to rejigger based on some other criteria like what you just said, or proximity or whatever, then you could regroup those. You may get sort of close and then refine it.
So really I have a whole graph that's 30 nodes, and it's just a matter of how I've chosen to issue the work.
Correct, and that graph of 30 nodes may be just a sliding window of, I could be in the middle of processing 10,000 nodes, and I've got 30 in the current window of things that's in between what's already been executed and what hasn't been yet presented to me.
Right. Okay, because I typically think of a graph as a ordered sequence of operations that I'm performing on my data. So it may not make sense to split a graph, or if you like, in this case, a subgraph. I might have a sequence of operations that perform some, I don't know, matrix transform. But if it's just a matter of when queues get filled and dispatched, then from my perspective, I still have my whole graph doing its job, or my whole subgraph doing its job, and it's just being broken up into pieces for execution efficiency or something like that.
Right.
Is that the right way to look at it?
I think so, and I think that as some of the UTK guys talked about, and I'm expecting Ronnie and company are going to talk about here too, you may have, for many of these linear algebra types of problems, kind of an arrival of work over time where you don't necessarily know what the work is, and you're not handed a single static description of the entirety of the graph. And so you have to just sort of chunk that up as you go. If you could wait for the whole graph and then partition it, or you could just kind of have a moving window.
Okay, thanks.
And so you may wish then to, after you have done some initial partitioning, to add some interfacing nodes. PowerPoint's crashing again. Start this. I need to reinstall PowerPoint.
So,
almost.
In the meantime, is it possible to kind of explain where hi-hat sits with respect to the user programmer and the system? Because I'm having a hard time when you say, when you want to reinstantiate, I don't know if you're talking about the programmer or you're talking about the runtime or the compiler. Is it possible to give us an overview of where hi-hat sits?
Yes. That's a missing context for this. That's a long-standing context. So think of hi-hat as being a low-level plumbing layer that doesn't have any smarts to it, that lives beneath a scheduler, beneath some other entity that's deciding what to do, where, when, and how. It's not generating the work. It's not ordering or binding the work. It just makes it so that if some other entity that whether it's something that's inside heterogeneous executor, or there's somebody in the application code or whatever that's going to go and do those things, it would essentially have the smarts. And then Hi-Hat is basically providing the infrastructure of, oh, you want to do this? Great. I'll provide the dispatch interface to be able to get to the plugins that can achieve those things for you. Does that make sense?
Yeah.
So I'm going to wrap up here to leave some room. Again, some of the key decisions we made here were some generic nodes with kind descriptors, wherein we, in order to be compatible with the rest of Hi-Hat, and we had to define some types anyway. We defined a set of types and used those. We're not using an explicit edge type. Create dependencies separate from nodes, which a number of people said, yes, that's really good. There's some design questions. Hi-Hat normally has said for normal nodes, you only have one incoming input dependence, and use special nodes like sync all and sync any to gather in if you have to do fan in or fan out. It's not obvious that that's the right thing to do in a more generic graph context, so we're looking at supporting both. There's some question about how is it that you would want to traverse things in these graphs, and we didn't go into so much detail in this, but how we distinguish the interface nodes and handling remote requests. So I'll see if there's, we wanted to squeeze in another addenda topic here, so and then I'm cutting short going through the rest of the detail. There's more information on specific types and so on here, and sort of what the actual APIs are. But we've kind of picked some positions on these. Does anybody have any concerns based on what it is we talked about to say, no, I'm worried that this won't work, or I think you should do things differently? Okay. So if not, we have can share that API with you. So if you're interested and want to give feedback on the specific reference document we have with that, be happy to get that to you and get your feedback. There are a number of us that have been meeting weekly to sort of work through some of these specific details of how we would handle graphs for specific applications. And so if that's something that you're interested in, we welcome your participation there as well. So I will, any other feedback here?
Quick question, Sergey. Hello? No, so, I mean, so far, the dependency, I mean, the edges which represent dependencies, they kind of enforce like some kind of a sequence of execution, right? But for example, how to handle cases when you have multiple nodes in the graph which represent some actions, which actually can kind of, they cannot be, so only one of them can be executed at a time. So in a sense, kind of a critical section of some kind of subgraph where only one node can be executed at a time. So how to represent this kind of dependencies?
That's a good question. I don't have that supported yet.
Okay.
So,
one of the things that we're interested in looking at and having some discussions about is sort of for OpenMP's notion of tasks, and trying to work with Tom Skoglund and others, mapping from one to the other to see how that would work. And that strikes me as something that OpenMP has that we may want to look at. Another comment?
Hi. So we've been trying to, so this is Tal from EPH. We've been trying to work with the hi-hat API in our context. And as we probably mentioned in one of our previous meetings, we are proposing some kind of or we want to propose some kind of a C++ interface for hi-hat. And so probably we won't have time for this today, but we have prepared a code sample with this proposed interface. Now,
awesome.
Yeah, so yeah, the goal is to support or to retain the full functionality of hi-hat, but also provide some wrapping classes to increase the ease of use. And so we've uploaded the sample, by the way. Martin, want to say something?
Yeah, as Tal said, we aim to have the same functionality as the C API, and also for some case, since our C++ objects or structures are mostly wrappers around the C objects, so we can always just fall back to C API if there's some very specific use case that we cannot support. But we aim to have, we aim to be able to write code which is, let's say, more user-friendly and more expressive in the sense that we can achieve the same goal but with much less code.
Great. Well, why don't we queue that up for another time to walk through that?
Absolutely, definitely.
Yeah, absolutely. I think we can discuss we have a meeting, but I wanted to mention the sample is uploaded on the Google Drive, so you can take a look and we can discuss it later.
Excellent. All right, great. So let's turn it over to Arya or Ronnie. Thanks very much. Sorry for compressing your time here.
Oh, that's fine. Okay, so I'm guessing you guys can see the screen?
Yep.
Okay. Okay, so I'm gonna briefly go over, so I'm Arya Chatterjee, work with Oscar Hernandez at Oak Ridge. We're looking at different physics applications, mostly with the SNS group and at Computer Science Research as well. And we just wanted to give a brief overview of the application that we are looking at and how we can use graphs or hi-hat as well going forward. So a couple of acknowledgements down here. I'm going to scroll through the intro part. So the application that we're looking at is, can everyone hear me properly? Yeah? Is the sound on?
Good.
It is on, yes, okay. So the application that we're looking at is DMRG++, which is a density matrix renormalization group. It's a sparse matrix, dense matrix computation. I'll show like briefly how the application works. And so we are mostly targeting our idea is to target everything on Summit and incrementally implement both on CPUs and then accelerators as well. So this is a code that has been running on Titan for the last 3 years now. So we're moving the code over from Titan to Summit. So the density matrix renormalization group basically gives you a deeper understanding of nanoscale material properties, mostly for superconductivity, power grid. Again, this is a collaboration between the material science group at the lab and CSR. As of today, what we have is DMRG is kind of limited to one-dimensional problems because of the size and the complexity of these algorithms as well. We use OpenMP, IBM ESSL. There's a MPI part, which is not that optimized, but we have an MPI version as well. So it's multi-node. So CJ actually sent a couple of, going back, CJ actually sent a couple of things in the email. I'm gonna try to answer those, CJ, as I go through the slides to the best of my ability of things that we know for a fact. So we're using Clang++ for DMRG at this point. We did try other compilers. There were some issues with OpenMP being implemented properly with GCC. and stuff. So that's why we kind of stick with Clang++. Moving forward, what we want to do, at least the physicists, what they want to do is focus on more practical materials that are more two-dimensional and three-dimensional problems, which would take up a lot of space, both memory and the computation. So you want to use these the GPUs and coordination between the GPUs when you're running this on Summit. Okay, so it's a common trend at the lab to design mini applications of bigger applications to try to accelerate the process of implementing things in a bigger application. So the mini app that we are looking at is Chronicle product. It's from the DMRG++. What happens inside, there's a matrix, two-dimensional matrix that we just multiply with the vector x here, and then you get a y. The interesting part is the Hamiltonian matrix, which is the C matrix that you're looking at on your left. The C matrix is what makes the entire application complex or easy based on how the matrix is. And we talk about some of the load issues and the workload in the C matrix. I'm going to go over the next slide, which would give us a better understanding of what the C matrix looks like. So each element in the C matrix is composed of two vectors, A's and B's. The length of both these vectors will be same for all indices of the C, but each element in these A's and B's are also a vector. So you can think of it as a vector of vector. But the vector elements in A's and B's can be of varying length. And that's how the sparsity or the density of the entire matrix is going to be defined. So what we are looking at on the right is so this is the same matrix. You can think of it as the first 4 blocks was the thing on the left, basically. So all your data is mostly clustered on the principal diagonal. Not mostly, it's always clustered in the principal diagonal. And your density of this matrix increases as we move closer towards the center. And your sparsity of the matrix increases when you're moving away from this principal diagonal. So this is how the load imbalance that happens, which I'm going to show in a few slides. But some things to point out with respect to the email as well. So there are no dependencies between any of the cells that we are looking at on the right. So every cell can be independently computed. But then if you're thinking of as like, if you're breaking it up as a task, there will be 2 levels of dependencies when you actually reduce, which I have a slide that will probably make it more clear. Is there any questions on this, on the sparsity density thing of the matrix? Okay. So threw in a pseudocode of what's happening inside. We currently use OpenMP though. We use multiple programming models actually, not just OpenMP. But so like lines 5 and 7 is where these are the reduction variables that we're using, and line 11 is where we use the dgem operation happens, and we use IBM ESSL. We currently use the non-threaded version. I don't know if people are familiar with how the threaded works, but if you use the threaded version, you always have to tell the compiler during compile time, basically, that how many threads you want to use for this ESSL using the OMP num thread. And the problem ends up being is our Hamiltonian matrix is not a balanced matrix. So if you use threaded ESSL, then you get worse performance because now it's running threaded for every cell. And we don't want that. We kind of want to dynamically change, and which is something that currently doesn't happen with the threaded version of ESSL. So if you think of it in a form, I'm trying to relate to graphs, and again, this is in relation to CJ's questions as well. So there's what we technically can do is make every cell a task as well, or every cell a graph in a node, every cell a node basically. And then there will be two levels of dependencies if we think of it with respect to the reduction. So one is reduction for that cell itself. So if you look at the Cij, each cell needs to be reduced first. So there would be a reduction on Yij. And the other one would be C0 through the entire row. So the full row needs to be reduced as well. And those two would be the only dependencies if you're thinking of putting every task as every cell as a separate task. But then if you club a couple of tasks, then you need to make sure there is some sort of synchronizations when you're reducing the row. But there is no dependency across columns, so you can technically have one row as an entire task as well. So we did use a couple of load balancing schemes when we were doing OpenNP using nested parallelism, task loops. We did a couple of tiling and stuff as well, but we didn't get the result we were looking for. Probably we didn't divide the work properly, and at the same time, we kind of needed different resource allocation for, when I say resource, is like the thread allocation for each of these workloads, and it changes over time, which brings me to CJ's point that he brought up a couple of minutes back, that even with graphs, like creating an initial graph and putting it in, for us it might not work because it's a convergence algorithm. So the matrix size grows over time, over this iteration. So you kind of need to have a different scheme moving forward for the, let's say, the 10th iteration or the 15th iteration. You might need a different scheduling scheme as well. Is there any questions with respect to how we do this? Okay. Okay, so a couple of things that we're looking at here is the load imbalance. And as from the picture before as well, the diagram on your left, what you're seeing is the work. So INJ, so your X and Y axis are basically the Cij matrix cells, and your Z axis is the work, flops for us at this point. And you see the maximum, the highest peak is in the center, and then your peak kind of dies down as you move away from the principal diagonal. So that kind of shows what we were saying 2 slides back with respect to the work. And the load imbalance happens on if you look at the diagram on the right, is majority of these cells, or we call it patches, have negligible work. But then there are a few patches that constitute most of the work. So if you have a singular scheme or scheduling policy, or the way OpenMP works at this point, is like even if you break it in different tasks, you would have the same resource for all the tasks. Those kind of things will actually not work for us, and we have seen it did not work. So we need to come up with something that's more, the granularity can change over time.
Just calling your attention till we have about 5 minutes left.
Okay, yeah. Okay, so this pretty much again shows the load imbalance of the application as well with respect to iteration, and over time it runs in different phases. Each phase is a different matrix size. So as you can see, the imbalance basically worsens as we move towards phase 5, which is like the last step for our convergence. And then on your right, what you're seeing is the overhead of using these OpenMP constructs. So the overhead is basically fork and join plus barrier minus work. So if you look at the 0 to 2000 iterations, that's the least work. And then we use the same strategy. So you would have way too much overhead of just using these fork join or barriers and stuff in OpenMP. So I'm gonna quickly go over one more thing. So we ran a couple of, so we did run on Titan, but this was a new run that we did on a Volta Titan GPU card that we have. It's a system that we are running on. So we ran it on two different system sizes. The thing to take away from here would be smaller system sizes have a lower sparsity of the matrix and then throughput's higher. Whereas for larger systems, which is what most physicists are interested in, have a higher sparsity and then you get kind of lower throughput. So the graphs, since I don't have time, I'm not going to go over it, but the slides are available online. And if you have any questions, feel free to ask. We also did batching as well because of these smaller DGEMs. So there's two different batchings we did. One is the batch one is on the CPU, the batch two is on the GPU. And then we did these DGEM calls and you're running the batched operations. So the problem with batching is like you have to rewrite the entire kernel to make sure that the batching, the coordination happens between these matrices. It will be something nice to have if a programming model is giving us that feature of batching as well. So we'll quickly wrap up with, I think I'm on time. So a couple of things that we looked at and things that we might need as well is sort of vector reductions. We use, most of these applications use vectors, which makes it interesting because not a lot of programming models will let you use vectors. You have to write your own user-defined reductions. Load imbalance is a problem for us. There are a lot of task synchronizations, and if you're doing tasks, then you need to have support for task reductions as well. Dynamic resource allocation, because of how our application changes over time, the matrix changes over time. Batch DGEM, we did it, we get better performance, but we want to have something that's a little more high productivity and less work on the programmer as well. And then use of hi-hat and CUDA, because we kind of need like a CPU GPU coordination as well. And this is something that I brought up before, is the multiple GPU. If we use multiple GPUs, we kind of need to do the reductions on the GPU rather than moving it down to the CPU and then reduce. And same thing for the last point as well, the inter-GPU communication on node without the interaction with the CPU as well. So,
and this is all single node at the
correct.
moment, right?
These are all single node. We are moving towards more MPI stuff as well, but at this point, I think it's more with the Summit Fat nodes. This application should be able to do on a single node. But there are applications that, the other application that I spoke with you about, that one is totally on multiple nodes. So, yeah.
Maybe I can give a little bit more additional information here. So DMRG++ can use MPIs because we are also doing ensemble simulations where these calculations are repeated for multi-frequencies and or in a set of model parameters. So basically, what Ronnie has been describing here can be run on one node, but when we multiply this can span 2,000 nodes around. So, and all these tasks are independent on different nodes.
Okay, great.
Do we have reached 10 o'clock? Do we want to wrap this up and pick it up again in a month from now, or are you finished? Would you like to have another opportunity to complete?
Ronnie, are you muted?
Sorry, yeah. Yeah, not sure. Was a question for me? I mean, that was my.
Yeah, it was, Ronnie. I was wondering how much more you had here.
No, that was my last slide. So
good.
Yeah.
Sounds good. Any questions for Ronnie before we wrap it up? Thanks,
I
Ronnie.
think in general, we're interested in looking at some specific use cases, and we think that there are a number of cases like this, potentially with some batched operations and sets of matrix operations that we may want to look at mapping onto graphs and working through some of those usage models in greater detail. That's a direction forward. Great. Well, thanks very much for jumping in and presenting on this. Folks from RNL, great work. And we'll look to picking it up more.
Yep, thanks.
Thank you.
Let's wrap it up, and thanks, everybody. Appreciate it.
All right, take care.
Take care.
Bye.